Thanks to the two Davids and Tom for that great introduction. Yes, working late into the night is very tough to do, but I had some friends around me helping me prepare this talk, and hopefully I'll make it through it. And I'd like to thank David Firakawa, who I've known, trying to figure out how many years we've known each other, but it's about 25 years we figure I first met Dave in the desalination. Now, my talk, I'm sort of going to give a little history of biofouling and its future, because I got my PhD degree at Columbia University, which is not known for desalination, but it is known for biofouling. And we worked when I was a grad student on heat exchanger biofouling and something called ocean thermal energy conversion biofouling. And my esteemed mentor, Dr. William Corp, who is one of the founders of biofouling, guided me, and we were supported at that time by the Office of Navy Research, because the Navy was very much interested in biofouling on the ship's surfaces because of the additional costs on fuel that the biofouling, just like what we see in membrane biofouling, the increase in energy I'll talk about today, the Navy saw it in terms of the increased fuel costs to move their ships when there was biofouling on the hull surfaces. I am now Professor Emeritus. My home university is Fairleigh Dickinson University. You might not know it in the world, but it's just outside of New York City. And it was the first university we got funded by the Office of Water Research and Technology of the U.S. government. We were the first university to give a bachelor's degree in desal engineering. And we were the first university to get funding support from the U.S. government to study pre-treatment biofouling and organic fouling in the mid-70s, and we were a subcontractor to a company in New Jersey called Permuted. And they built the first seawater RO plant in Gaddafi in South America, Venezuela. And that's where it all began. Okay, so I just want to give you a little history, because biofouling is not new. It's been around, and you can see that it all began in 1943, so it's about 70 years old, the study of biofouling. And a great microbiologist, Claude Zobel, and you can read his papers on biofouling. He was at the Scripps Oceanographic Institute in San Diego, and he is what we refer to as the father of biofouling. His first studies showed that when you put a surface in seawater, the first thing that happens is that there is an organic coating to the surface, followed by the attachment of bacteria. And the bacteria attached because of the fact that the glass surface became organically enriched, and the bacteria will always go to where the greatest food supply is. They're no dummies. And they'll attach to the surface, because in the planktonic form, in seawater, the nutrient levels are so low, it can't support the growth of these organisms. And so the attachment to a surface makes a nice place for them to find an enriched organic surface. Then in 1970, and I had just finished my grad studies, a fellow at the University of Buffalo, Robert Bayer, said the first event and he used a germanium crystal and showed that if you put a surface into seawater or any aqueous medium, the first thing that happens is there is a chemical conditioning of the surface. And this is in forms of, he said, are humic-like glycoprotein material that were present in the seawater. And before any bacteria can attach to that surface, the surface has to pick up these glycoprotein type material from the seawater, and then the bacteria will bind to those organic substances on the surface. So in 1970, Robert Bayer was a very important study. And so immediately you can see if you can interfere with chemical conditioning, you interfere with the attachment of bacteria to the surface. And this is a very important way of looking at how to combat biofouling. Then in 72, two lobes, it's not the Sydney lobe that we know who developed the first RO membrane, but a different lobe. Lobe actually isolated these glycoproteins and identified them as very much like humic material, very acidic material, contains high concentration of uronic acids. And so now we see that it's very important that these organics are involved. And my mentor, William Corp, and I postdoc also with William at Columbia University, then showed that the way the sequence goes is you have a chemically conditioned surface, and then you have certain organisms that can attach, and I'll talk about those attachment mechanisms, which are called primary colonizers, and then they produce their own EPS material, acidic EPS, and then there are secondary colonizers, and the secondary colonizers outcompete the primary. So the primary, which initiates the biofoul, if you were to, quote, do an autopsy, you never see these organisms anymore. You start to see the secondary. And the secondary organisms are organisms like Colobacter, Hypomicrobium, very specific organisms that can now, after the primary colonizers are formed, can start producing the matrix, the acidic EPS, and these glycoproteins polysaccharides. Okay, in 75, something called OTEC, if you're not familiar, Ocean Thermal Energy Conversion, came about. And it was the Department of Energy in the US put millions of dollars. If you were doing OTEC work, you got tremendous support. The problem with OTEC, and it's based upon the differential between the surface water temperature and the water temperature at the bottom. So there's, say, 0 degrees at the bottom of the ocean and 30 degrees at the top. And that temperature differential, if you put it through a turbine, the heat differential generates energy. However, there's a heat exchanger that is needed, and of course, if that heat exchanger biofouls, you lose the efficiency. And although the engineers at that time, when I postdoced with Bill Corp at Columbia, I was involved in biofouling of ocean thermal energy conversion systems. And engineers are always great because they come up with equations, and they said biofouling is not going to be a problem with OTEC. And the reason they said that is because they were getting the tremendous funding, and they wanted to keep continuing. But we said, Bill Corp mainly, who was saying, it'll never work because if you can't solve the biofouling problem, you can't get the efficiency needed for ocean thermal energy conversion. And indeed, OTEC never came about. The best the Department of Energy could achieve was in Hawaii, and they created enough energy for generating 1 light bulb of energy, and it met its death. Why? Biofouling. Then in 78, I joined Fairleigh Dickinson University in 1970, and there was a guy there, Bob Backish, who probably David remembers Bob Backish, because Bob Backish formed what was called IDEA. Of course, today we have IDA, but in those days, in the 70s, it was the International Desalination Environmental Association, IDEA, and it had its headquarters at Fairleigh Dickinson University. at my home university, and Bob Backish was the president of that time. And then, of course, IDEA eventually became what we know today as IDA. But I remember Bob Backish coming over to our department, and he had just gotten a grant from OWRT as a subcontractor to the company Permuted, who was building the first seawater RO plant. And Bob says, does anybody know about, in this department, biofouling, because the government is interested in preventing the membranes from biofouling. I said to Bob, well, I've worked on biofouling, don't know what a membrane is, but I know about biofouling and heat exchangers, must be very similar. So my start into biofouling was around 1975, and we published the first papers. And we had a marine lab in St. Croix, U.S. Virgin Islands, and we set up the first seawater RO pilot plant where we studied biofouling. And I didn't know anything about seawater RO. The company Permuted was building this big first seawater RO plant in Venezuela, and they were concerned that the membranes might foul. They were using DuPont B10 hollow fine fiber polyamide membranes. Okay, so if you're probably just familiar with the spiral wound, but in the days of my youth in seawater RO, hollow fine fibers were the membranes that were being used. No spacers, you didn't have to worry about thickness and configuration of spacers. It was just a hollow fine fiber membrane that was produced by the DuPont company, and they were in the business until the late 90s when DuPont decided it wasn't profitable for them to make what we call the permacept membrane anymore, and they went out of business. But we published the first paper on membrane biofouling, and I remember saying, and Permuted said, oh, this is a success, but why was it a success? I said, you know, I see a lot of fouling on the membrane. Oh yeah, but we can clean these membranes, and as long as you can clean the membranes, you know, it's great. But it wasn't great. Biofouling was still a big problem. And what happened is in the early 80s, DuPont started to really build some big seawater RO plants in the Middle East, and tremendous problems with biofouling, okay? And DuPont came to me and said, okay, you sort of know something about biofouling, can you help us out in the Middle East? And then we started to work and identify that one of the major problems in the pretreatment was with the chlorine dechlorination. We didn't know why at that time, and we still don't know why, but we came up with some promising studies that said the chlorine degraded organics, humic-like material in seawater, to AOC, assimilable organic compounds, and that when you dechlorinate, then you could have produced food for the bacteria. Okay, so with DuPont and myself, we produced a means of producing chloramines in seawater rather than chlorine, because chloramines don't degrade the humic acids into AOC. The problem with the chloramine is that you have to add ammonia to seawater because the concentration of ammonia in seawater is very low. And one of the first plants I remember in Dubai, you depended upon the operator to use a certain amount of chlorine and a certain amount of ammonia to get the monochloramine, and the operator says, and we didn't know that, but he kept pouring in more chlorine because he was trained that chlorine was good, and of course we weren't producing the monochloramine, so that was a problem.